Lent Physics and Maths Society, as you can see, because please work out. Mr. Sheils is talking today on the geometry of the planets. You can clap that if you want.
Thanks very much, and thanks for the Maths and Physics Society inviting me to talk to you today. I put this poster up to maybe inspire you to come, to wonder what these diagrams might be, and here I've revealed that they are by Johannes Kepler from 1596 and Isaac Newton from 1687, but you'll see what they mean later on in the talk. The talk will mostly be a story, and it will be a story about how, since the infancy of our species, and we guess our species is between 100,000 and 250,000 years old, since that time we have been constantly trying to look between the dark patches of the night sky at the dots and to try and join the dots together. And these are photographs of the same section of dots in the sky from different parts of the world. And you may have spotted the pattern. It is that one. Oh, I will go back now. It is that region there, which is the constellation Orion. However, it wouldn't have always been called Orion to different cultures at different times. I'll give you a different example of how cultures may join the dots. This is the constellation Ursa Major, although that's what we call it now. It's not always been the case. In fact, mostly in Britain we recognise this pattern, which we call the plough. In northern England, some people in medieval times did not call it the plough. They recognised this pattern, they called it the butcher's cleaver, slightly violent alternative. In North America, again, a different pattern, similar shape though, and they called it the Big Dipper, or a large soup spoon if you like, and that is a Big Dipper created out of the horn of a goat. In other parts of the world, they would have recognised it as this. The French would have called it la casserole, which means the saucepan. Still further, we head to Germany, and they will call it Karlswain, or a man's wagon. Further afield still, to China, they will have recognised it as this, and it will have been the transportation vehicle for the celestial bureaucrat who would go round and collect monies from riding on a cloud. You probably, if you know a little astronomy, will recognise it as Ursa Major, which means the Great Bear. So what we were looking at is just a small part of a larger constellation that's called Ursa Major. However, perhaps the most shocking one and the most adventurous to our modern viewpoint is this arrangement, which you may not be able to immediately guess what it is, and I think you'll be surprised to see what it is. In 1200 to 1300 BC, the Egyptians had mythology regarding the sky, and this is a photograph of Seti I's tomb, and we're going to look at this particular pattern here. And it is believed by some anthropologists that the pattern you just saw represented a bull, a man on his side, and rather astonishingly, a hippopotamus with a crocodile on his back. Now, it is neither self-evident to you or I, or perhaps any other culture other than the Egyptians, why that is the case. And in fact, it has been disputed by historians for over 100 years, the exact location of these stars. Nobody is quite sure whether it is in fact Ursa Major or different places. I think it's rather ironic, and it highlights the fact that you can pretty much, with enough imagination, draw anything, anywhere in the sky, as there are around about 24 proposed sites for this constellation. So, that is Ursa Major. For thousands and thousands of years we were placing pictures in the sky, partly as a guide, a way of being able to tell different parts from each other. The indistinguishable dots suddenly took form and were easy to remember. Some cultures probably did in fact believe that there were real gods up in the sky, and it is difficult for us to say now with our view. However, it did take a long, long time before, rather than using the sky as a canvas for which to paint on with our own imagination and our own ideas, that we saw it worthy as a subject of art and a subject of science to study in itself. And here's a vanguard of Ursa Major. I'm sure you can see the constellation. That, of course, isn't true just for Ursa Major. Here is a simulation of tonight's sky at around about 8:30 p.m. And if we join the dots, this is the modern joining of the dots with our constellations from astronomy. There are their names, and there are their shapes. Rather elaborate, I'm sure you'll agree. And I think if you look at 8:30 towards the east, you will see Ursa Major tonight. Now, after that, people began to study the dots that moved. They of course all move in the night sky, but they all move as one together. After some time, people noticed that there were patterns amongst the ones that moved. And the ones that moved they called the Wanderers, and we keep that name, although you may not recognize it. We call them the planets, and the planets in the Greek means the Wanderers. I'll show you an example. I'm going to show you a very particular example from a particular time and a particular place, so you'll have to bear with me. We are going to look at 1595, and we're going to look at the 23rd of August, and it will be 10:30 at night. That will do. That will do me. So what I shall do now is take away the constellation pictures. I'll leave perhaps the names, and we're going to look at the planet Mars. I want you to watch it as it moves through the sky day by day. I can advance the simulation by one day, so we are at the 23rd of August, now we're at the 24th. And we're going to go one day at a time. I want you to watch it as it moves through the sky. I'm going to go rather quickly, and I will adjust the camera as we go. Notice the background stars move as the Earth is orbiting the Sun. They appear at different points in the sky depending on the time of year. Now, you may not have noticed anything necessarily peculiar about that particular pattern, but I'm going to show it to you again from a slightly different point of view. I'm going to show it to you for historical reasons from where it was originally observed on an island called Alleyn in Sweden, and I'm just going to put the date back manually like this. I said it was the 23rd. This time, however, I'm going to rotate the camera with the sky. So now the camera rotates with the night sky as I go round. So I am looking for Mars, which I shall type in here. Where's Mars? Oh, so it hasn't come up yet. That's no trouble. Let me advance a little bit. Or am I too late, perhaps? Oh, no. Go further forward a bit. Oh, I think I have typed in the date incorrectly. Bear with me. 1595. You see the difference? It's important. I'm very sorry. You'd think that would have no effect, but you see it did. And I wanted the 23rd at 10:30 p.m. we go. So I will search again for Mars. Great, just where I was hoping it would be. And now what we're going to do is we're going to fix the camera onto the background star. So I'm going to fix it onto Aldebaran, and I can do that here. Center on selected object. I want to select this guy. Oh, rather strange. Okay, well I will do it manually. And we're now going to track the planet. Watch it as it approaches Aldebaran. Seems to change direction, move away, and I'm advancing one day at a time, and then seems to go back in the other direction. So not only did the planets wander throughout the night sky, they seem to change direction in a very puzzling manner. And this is a topic that has lots of sticky consequences. People thought that if the Earth were at the centre, you'd have to cook up loads of very difficult geometry to explain how that's possible. If you think the sun's at the centre of the whole thing, then problem solved. The geometry becomes a lot easier, and that's what I'm going to focus on now. If you look at this image, this is the same thing, but it's a composite photograph. The photograph has been taken a few days apart, pointing at the same patch of the sky, not necessarily the same direction, because the sky will have rotated depending on the time, and it's a difference of several months between the beginning and the end. Notice the planet Mars loops the loop. Well, we can explain this. If the Earth's on the inside track, a closer orbit than Mars, then we can explain it by saying that the Earth's orbit is faster than the Martian orbit, and this loop-the-loop, or this retrograde motion as it's called, can be explained by just our particular point of view. I'll try and show that to you again. Let me advance on a little bit. And it is, if you follow the line of sight of the Earth, explainable. Now, once you know that there are orbits for these planets, or you guess this, it's an interesting question to ask, well, what are they? What are the distances? If we have the unit of the Earth's orbit around the Sun, the distance from the Sun to the Earth, and we set that as 1, we can then try and find the ratios of the orbits of the other planets. Is it possible? And part of this talk is to show you how it is possible. So, let's take the Earth. Rather than Mars, I'm going to start with Venus because the mathematics is simpler. So we've got the Earth in its circular orbit, we'll assume, and there is the orbit of Venus. I'm not quite sure how far away it is, but it's definitely on the inside, I'm going to say. I'll explain to you how I know it's on the inside. There's Venus. The way I can find the distance to it is I can ask the question, when is that angle, how big it looks in the sky? When is that at its maximum? And it does get a maximum. It stays close to the Sun. It doesn't wander off towards the other side by any means. Set time to now. There's now. I'll advance a little bit. Well, I think I'll go back, in fact, to... I'm going to search for Venus. Over there. And let's go back so we can see it in the sky. There. So there's the Sun and there's Venus. And by coincidence, the talk I'm giving today, we are round about at the correct time where Venus is as far as it gets in the sky from the Sun. It'll start soon in the coming weeks to head back the other way, and then will reach its furthest point on the other side. That is called, if you like words, the greatest elongation of the planet. And this occurs, and I'll leave it to you to prove it, but it occurs when the angle between the Sun, Venus and the Earth is 90 degrees. Well, we can do this because you know trigonometry. That is the hypotenuse, that's the Earth's orbital radius. That is the opposite angle, that is Venus's orbital radius. All we need to do is measure that angle, and we can get the ratio of the orbits. Well, you can do this early morning, if you like, tomorrow, around about 11 o'clock in fact. Don't look directly at the Sun, of course, you can do it with shadows. Cook up a clever way. I can do it on a simulation here. And I get around about 46 degrees, which is good, because I prepared my slide. on the basis that it was that. And if we have 1 as the distance here, because I don't know what it is, we'll leave that to someone else to figure out. If I say it's 1, I can figure out the ratio at least, and then the fraction disappears, and I put in 46, I get 0.72 as the ratio. So that's how I can do it for Venus. I can do the same for Mercury as well, that's on the inside. But how would I do it for the outer planets? Well, it's a little trickier. For the outer planets, you need a little bit more mathematics, but you're capable of it. It's still the same geometry, but it's just more tricky. So, look for a time when the Earth, the Sun and Mars form a straight line. That's called opposition, with Mars being 180 degrees round from the Sun. Then wait. As the Earth, we said the Earth is on the inside track, it's also going faster. So it'll advance further. Wait for a time when you get a 90-degree angle between the Sun, the Earth, and Mars. That is called quadrature, if you like, big words. So we've got the orbital period of the Earth will be however many seconds it takes to orbit. We know it is 365 and a quarter days. And if the speed of it orbiting around is constant, I can say that it does 360 degrees in however many seconds that is, e seconds. And that's an orbital speed. If I assume the orbital speed is constant, then I can say that that angle divided by however much time it took to go from there to there must be the same number. I can rearrange that, and I get an expression that gives me that angle. So if I measure the time between the opposition and the quadrature, I can figure out what angle I've gone round the Sun, or we have all gone round the Sun. Mars, however, hasn't gone round as far because it was going slower, and I can do, if you look at the bottom, exactly the same mathematics, but with Mars saying that angle beta divided by however many days it took for that to happen, 360 divided by however many days or seconds it takes Mars to orbit, and I get an angle beta. Now you will notice that we do have a right angle triangle on the diagram, and I would need that angle alpha minus beta. It looks like a bit of a monster of an equation, but it's not. It's quite simple. And I'm going to put it up there. And I can now use trigonometry once again, because I have a cosine relationship between the Earth's orbital radius and Mars's orbital radius, and I put 1 as the orbital radius of the Earth, and rearrange, and then substitute in, and I get that. And that does allow me to calculate the orbital radius of Mars if I know how long it takes for the Earth to go around the Sun. Well, we do. It's a year, yeah? And if I know how long it takes for Mars to go round. I don't know that. So that's going to take a bit more work. Here's a way you can figure it out. Opposition again. Wait for that moment. Then figure out how many days it takes until that happens again. Now we said Earth was on the inside track, so it's going to be going faster. So first of all, it's going to go past Mars. It's going to have to go all the way round again before opposition occurs. So we know that time is going to be more than 1 year, but we're not quite sure what. So I can do the same equation, 360 degrees in e days or e seconds, however I choose to do it. And it'll be this angle phi divided by, well, it'll be however much time. I've called the time s this time rather than capital T to distinguish. But I will have gone round the orbit once already. So I'm taking away 1e from it because I know that that doesn't count. I rearrange the angle and I get that. And all I'm going to do is look at what that would be for Mars. Well, Mars didn't go all the way around, it stayed where it was. So I've got another expression in terms of m, and I get the same angle. So they're obviously equal. They're talking about the same thing. And I've got that. Don't worry if you can't follow the steps, you just need to know that it can be done. And there it is, rearranged, still further rearranged, and once more. So now that's an expression of the orbital time period of Mars, if you know the orbital time period of the Earth, which we do, it's a year, and the time for these two oppositions to occur, and you can wait for it to happen and then measure it. So, we now have the orbital time period of Mars. Can we do it for Venus? Well, that's actually really easy, but it requires a little leap of the imagination. It's exactly the same thing, except that we're now on the outside. We're on the outside track. So what I need to do is take that equation above and substitute Mars for the Earth, because the Earth is now on the outside, and substitute the Earth Venus, because Venus is now on the inside. And I do the same again. I wait for this opposition to occur, this time with the Earth on the outside and the Venus in the middle. And I get that expression where it's pretty much the same, except there's an addition rather than subtraction. So I now have a method of calculating the ratios of the orbital radii and the time periods. A man called Nicolae Copernicus did this in the 1700s. He got that by Copernicus, and then the second column, the modern results. Not bad for somebody who didn't have a telescope. This is just measuring angles. And I wanted to show you that it's possible, just with basic trigonometry. Right. So Copernicus has joined the dots in a slightly different way. He hasn't joined the dots of the background stars. He's looked at patterns between various observations and assumed that the orbits are circular. It took a little while before somebody asked another interesting question, and he asked, why are they like that? Why are the numbers those numbers? And the rest of this talk will be focused on these two gentlemen, Johannes Kepler and Isaac Newton, who I'm sure you're familiar with. The latter, perhaps not the former. The former published a tremendous amount of work, and we're fortunate that he not only published his results, he published how he did it and how he was thinking, what he was thinking at the time. Sometimes he had rather crazy ideas to our modern ears, and they are in orange there, and I will speak about one of them. But the ones in purple, they are perhaps the first modern physical theories and the beginning of what we now call physics. When Kepler was worried about why the orbits are in a certain ratio, he was very knowledgeable of mathematics. And these are called Platonic solids. They are tessellations of regular polygons, but they have to fit over the surface of a sphere. They have to close up. Not in the same way that you have a wallpaper tessellation that's flat. These curve. What is interesting is that you only have 5, and it's a separate talk to prove that to you, but there are only 5 in existence. And Kepler thought to himself one day, isn't it astonishing? It can't possibly be a coincidence. There are 5 Platonic solids, and there are exactly 6 planets. It's amazing. I'll show you more. He drew this diagram to explain himself. He said that the sun is at the center, and if you draw these Platonic solids in between the orbits of the planets, you can account for their ratios. And he said that is why it's perfect. It's mathematically perfect. There's the center zoomed in. I'll show you exactly what that means with a simulation. However, you can buy a paper model kit that I'm presently ordering. I hope to try and build this maybe next free time I have. And somebody has tried to make a simulation based on that paper kit. I want to show that to you now. So here we have the sun in the center. This is what Kepler thought. He thought you draw a octahedron around the sphere that the orbit of Mercury creates. So you imagine the orbit as a sphere rather than just a circle, and you draw an octahedron around it. You draw an octahedron around it, and then you draw another sphere around that, so that the sphere touches all the points of that orbit. Then you get the orbit of Venus. You then, with that sphere, put the next one so that all the edges touch that sphere. That is icosahedron. And I will now zoom out a little bit. You then, around that, put the dodecahedron, and the sphere in between is the orbit of the Earth, and you see the moon there. Zoom out still further, and I put another sphere around the dodecahedron, and I can fit a tetrahedron around that. That's the orbit of Mars. And then once again, I get the orbits of Jupiter and Saturn in blue around that. That's the diagram he drew, and I think you'll agree it looks rather similar to the diagram there. So he thought he'd cracked it. He'd solved it. However, compared to what we now think of physics, it was a terrible mistake. he was comparing a physical variable, a set of data, with mathematical objects, these platonic solids. And he was using mathematics as an object to compare with a physical variable. When he got some more data, which he got from the master observer Tycho Brahe, when he got some data from that, he found that his theory was incorrect. The orbits weren't quite what he thought they were, and it all began to break down. He spent his entire life trying to get it to fit. And in doing so, he pored over an immense amount of data on the orbits of the planets, trying to find patterns. When he did get it right, he did this. He compared the orbits, not with a mathematical object, such as the platonic solids. He compared it with another variable, the time periods. And he found, just through sheer creativity, work and imagination, that if you cube the radius and you divide it by the time period squared, you get pretty much a constant number. He was astonished. He said he thought he was dreaming, and he was absolutely certain that this ratio meant something. That was the beginning of physics. Rather than using mathematics as an object to compare with physical variables, he started using mathematics in order to compare two physical variables to one another. He came up with these three laws. He said, in fact, if you study the new data, the orbits aren't circles, they are ellipses. He found the second idea, which is that if you look at two time periods between an orbit, the area stays the same. People say equal areas in equal times. I think the simulation will make it a little clearer. If I take the orbit of the position of the planet and I imagine where it would be, say, 10 days later or 2 months later, and I keep that time interval fixed, then the area swept out by the orbits remains the same. The planet is slower when it's closer to when it's further away from the sun, and faster when it's closer, and this keeps the area the same. The last law was the one I just showed you, which is the relationship between the radii and the time periods. Now, he'd cracked it. He'd found a physical law. However, it seemed a rather peculiar thing to figure out. It didn't seem to be connected to anything, and he didn't really mention it all that much in his own writing. He much preferred the platonic solid idea. It took the genius of Isaac Newton to see the value of what Kepler had done. And this is the last geometric demonstration I want to show you. Isaac Newton devised a way of explaining the elliptical shape of the orbits and explaining the relationships by saying there is a force directed towards the sun that causes the planet to orbit in this way. Now, Kepler had thoughts of similar ideas, but he'd never been able to get it consistently together. And he certainly never was able to demonstrate that a force towards the sun meant that the planets behaved as he saw. So, Isaac Newton's law of force, I don't think I'll need to explain it to a lot of you, but the idea is that forces are the cause of accelerations. Fairly new idea, in fact. And they act on objects, they act from where the force is experienced. You can add two forces together so that you can imagine that the result is just one single force. And similarly, you can take one force and imagine that it is composed of several that act on the object. So that was his method. That was what he was telling you to pay attention to. Pay attention to the accelerations. That's what counts. And he summarized it like this. If there's no force, there's no acceleration. If there is a force, then it is directly proportional to the acceleration. And the forces occur in pairs. They're interactions between two objects. Those are Newton's laws of motion, and I leave them for you to look up if you are unsure. That was generally, specifically relating to gravity and the motion of the planets around the sun. He said there is a force directed towards the sun, and he could even tell you what it was like. It depends on the inverse square, 1 over the square. So in the remaining minutes, I want to show you another application of geometry. Isaac Newton invented calculus. He invented differential integral calculus along with Leibniz. But when he was writing his book, he couldn't guarantee that everybody reading it would be able to understand him in those terms. So he concocted a geometrical proof that if you take Newton's laws of motion to be true and you assume that the force is directed towards the sun, then you get Kepler's law as a result. This equal areas and equal times. In other words, if you say this, you are at the very least also saying what Kepler says. And in fact, you'll see that Newton is saying very much more. Here is the diagram that Newton had in his original book. This is the Principia Mathematica, the original copy. And on page 37, he's drawn this diagram. As you can see, it's written in Latin, and I assume that not everybody in the room is fluent, so we'll focus on the diagram instead. And I've enlarged it there for you to see. And I have changed the colours a little bit. I'm going to do that slide again, because that slide in itself took maybe 3 or 4 hours. So it's getting a second viewing. There it is. And I'm going to take you through what it means, and then a proof of what Isaac Newton was claiming. The diagram refers to a planet orbiting the sun. Rather than consider the continuous motion of the planet orbiting the sun, he breaks it down into small chunks. He says, at the very beginning, the planet is heading on its merry way, starting at A, and we're going to assume that for the first time interval, no force is experienced by the planet. And it travels from A to B. No force, no acceleration, so it goes in a straight line from A to B, with accordance with Newton's first law. In the second time interval, it would, if there were no force, it would head up the same distance, because there's been no acceleration, in the same direction, so to BC. However, we're going to say that at the end of each time interval, the planet gets a little kick from the sun. In the direction of the sun, it's that line BS there. And these aren't forces, these are representing displacements and changes of displacement. And I'm saying that BS represents a change in displacement. So we've got the displacement caused by the force directed towards the sun, and we also have where it would have gone if there were no force. What Isaac Newton says is that what you do with vectors is you add them together. So that is caused by a force, Newton's second law. You should add them together as follows, as I showed in the previous diagram, and you get where the planet actually does end up, which is at capital C. This is what the diagram means. So once again, the planet, if uninterrupted, would have headed on the orange path, but it travels on the red path. And to highlight that you could add the vectors in both ways, you could do the small one plus the big one, or the other way around. He's drawn a parallelogram, which you see on the original diagram. Yeah. So we carry on the procedure again. If uninterrupted over that time interval, it would have headed up there, but it doesn't. It goes towards the sun and is shifted that way, and so on, and so on. I realise the time pressure, so I shall be brief. That's what it means, but that's not what we were here to do. We were here to prove that if you take the idea that the force is directed towards the sun, then you get equal areas in equal times. Well, that's what we have to do then. We have to show that the two triangles have equal areas because they occurred over equal time intervals. And it may seem like a daunting prospect, but it's actually rather simple. We're going to break it up. We're going to say, we're going to look at the first triangle, and we are going to consider the orange triangle. And if we can make those two equal, and then make the orange triangle equal to the second blue and red triangle, then we're done. So we're going to break it down into two steps. Well, first one is rather easy. They have the same base, we know for sure, because they were travelling at the same velocity. That's Newton's first law. Well, and they have the same height because I could make a line parallel to that, and then we have the same height. So that's done. Mathematicians like drawing a little square when they've done something. So proof. Notice that that applies even if there were no force at all, and that would just apply as the planet keeps going. If you want to ask me what that means later, please do. Now we have to figure out that area. SBC and SB capital C show that they're equal. Well, that's just as easy because they have the same base, SB, and they have the same height because we made sure that that green line was, when it was at capital B, was pointing towards the sun. So CC is parallel to BS, and therefore those two areas are equal. Notice though that if the force were not directed towards the sun, those two areas would not be equal. So it only works when the force is directed towards the sun. And I should skip that due to time. Isaac Newton then, with just that simple geometry, proved that the equal areas are swept out in equal times in accordance with what Kepler guessed from his observations. So in conclusion, we have had a journey from joining the dots together in the night sky to looking at the ones that moved. With that, we can make observations, and with the guess that they travel in circles around the sun, we could find their radii. With greater imagination still, we could try and determine why there are in certain radii. It turned out that that was a fruitless avenue, a confusion as to what physics actually was, a comparison of physical variables rather than of physical variables with mathematical objects. Once that was straightened out, it was possible to use geometry to explain the patterns, not simply to say what the patterns were, and Isaac Newton explained them in terms of forces. He was able to explain Kepler's 3 laws of motion of the planets around the sun, but he managed to do much more than that. He managed to say something that applied to everything in the universe. And with this, we were able to travel to the moon. We have been able to send probes to Venus. We have been able to send a probe to Mars. And we have been able to look up close at those dots we were seeing and trying to join in the sky, realizing that when we were trying to join them together, we didn't get anywhere near the beauty and creativity of just looking at them individually. Thank you very much.
I don't think we have time for questions.
No.
The bell doesn't go in here, but it would have gone a couple of minutes ago. But I just want to thank you. That was great.
Thanks very much.
And thank you everyone for coming. I don't know what's going to be on next week. Hopefully something.
Thanks for coming.
Just the red button.
Yes, please.